to lesson 32. So we're going to start looking at inference for a categorical variable. Over the last few weeks, we've been specifically focusing on quantitative variables, usually one quantitative variable for one population. Now we're going to look at when we have a categorical variable, specifically with two categories. So before we get there, we have a couple review questions from the previous week when we looked at t-methods. So this first review question, we have a sample of 12 observations and we put it into this histogram here. We want to know, given what we're seeing in this histogram, is it appropriate to use t-methods? I recommend giving the video a pause here, try and answer this yourself, and then I'll go through the solution. Okay, so a sample size 12 is fairly small. So that indicates if we want to use t-methods, the histogram has to look pretty good. It should look symmetric, maybe roughly normal. So looking at this, it does. I could probably, draw a line right down the middle, and it does look roughly symmetric. It does have one peak. So I would argue it would be appropriate in this instance to go ahead and use the t-methods. Even though our sample size is 12, 12 is probably going to be big enough. The t-methods are robust enough that this is going to work well. So review question 2. It's a similar question where we have a sample of, this time 21, and here's our histogram of the 21 in our sample here. Specifically for yearly advertising budgets in millions of dollars. They randomly select 21 companies from what list I'm not sure. So we have a stats student. They want to create a confidence interval for the mean advertising budget of all companies. So they're looking at this histogram and they're trying to figure out, can I use t-methods to calculate this confidence interval? So give you all a second, press pause, give it a go. Okay, so before we go anywhere, 21, it's not large. It's not really tiny, but it's really not very large. So it's definitely going to matter what the sample data look like. Because remember, if you have a representative random sample, that means your sample looks roughly like what your population looks like. So if my population looks like this, it looks like it's pretty skewed. I would say skewed right, and it looks like we have some high outliers. This should definitely set off alarm bells. If we have something that's very skewed or has extreme outliers, we're going to want to have a large sample size. Definitely at least 30, but probably more than 30. So looking here at our options, yes, because the data were from an experiment. Honestly, this sounds pretty observational to me. They weren't applying any sort of treatment here, so I would argue that it's not even an experiment. Yes, because the sample is large enough. When you have 21, but it looks this skewed, I would argue it's not large enough here. And I would say no, because the data are skewed and have outliers, and we don't have a big enough sample size, considering it's very skewed and has outliers. So I would argue C, but just to make sure, D says no, because the sampling was not repeated enough times. So, I think they're asking if they were to go ahead and take another 21 and another 21, not to make it a bigger sample size, but to do it more times. So I would argue C is our answer here. A sample of size 21 is just not going to be big enough if the population we're drawing from is going to be skewed and have high outliers. Okay, throwback here to about week 2 or so when we were looking at quantitative variables versus categorical variables. For the past few weeks, we've really been focusing a lot on quantitative variables. So think like variables that it would make sense to take an average of versus when we have a categorical variable. So maybe you might ask folks, what is your eye color? Or what political party are you registered with? And when you collect that kind of variable, a lot of times we might summarize it with counts. So we might say, okay, well, this many of the individuals responded that they have brown eyes. Percents is also common, and proportions. We're really going to focus on proportions. It is easy to go in between proportions and percents. Just know for calculations, it's going to be easier to stick with proportions to get things correct here. So then notation-wise, P is going to be the notation that we use to represent the population proportion. So when I want to talk about maybe the proportion of all OSU students that have taken out a student loan, that would be a population proportion. And so it's the proportion of units in the entire population that has that characteristic of interest. Then you have P hat. So if I were to take a sample, this would be the proportion of all individuals in that sample that have that characteristic of interest. So I want to just point out here, it's the number of, you can't see my air quotes, successes in the sample over n, which is the total sample size. So keep in mind, we say successes. What we mean is this is these are individuals or observations that have the characteristic of interest. Note, it does not have to be something that we traditionally think of as successful. You might want to say, well, what proportion of COVID tests are positive, right? A success in this case would be positive cases. So it's more of just this characteristic is present, that kind of idea. And then just to kind of reiterate here, a proportion, you can think of it as an average of zeros and ones. So if you assign a 1 to your successes and zeros to your failures, and I'm doing more air quotes, then you could take an average. So suppose I had 3 out of 5 folks have brown eyes out of 5. I could think of it as an average of, well, person 1, person 2, person 3. Doesn't matter really what order though. And then we had 2 folks that didn't have brown eyes, right? Out of 5. I'm still going to get 3/5, and that's going to be about 0.60. So you can think of it that way, where you assign your successes 1s and your failures 0s, and it's the same as taking your average. And what's really cool is a lot of the properties that we applied to means also apply here. So now we want to talk about the distribution, because when we repeatedly sample, we need to know, how does that sample proportion behave in the long run? How much does it fluctuate? So we can do things like estimate or test proportions. So we start off, we have a population and we want to know some population proportion P. So maybe I want to know the proportion of all OSU students that have a student loan. So then I'm going to go ahead, I'm going to take a random sample, and from that sample I'm going to calculate a sample proportion. So a P hat, and I can use this to estimate, and I'm going to repeat this. Take another random sample, take another, and then when I start plotting these, and I just repeatedly do this, take all the unique samples of that particular size and calculate the sample proportion from each of them, you end up getting a distribution or a sampling distribution of P hat. So things that are really useful is the mean of this distribution is P, so that true proportion. And then we also know what the standard deviation of the population looks like. So it's the square root of P times 1 minus P over N. And what is even cooler is if we know that we have a big enough sample size, the law of large numbers kicks in, and that tells us not only do we know where it's centered and we know its standard deviation, we know its shape. If we have a big enough sample size, the sampling distribution of P hat is going to be approximately normal, which we love, right? If it's approximately normal, this means that we can go ahead and we can calculate a z statistic and use the z table to find p-values. So not as only normal, it's normal with mean or center p and a standard deviation of this value here. That's square root p times 1 minus p over n. So the question or the example that we're going to use throughout this lesson, the next couple of lessons, you might remember way back at the beginning of the term, I asked a question on that student survey. So no one can have perfect weather all the time, right? I mean, ideally you could, but So just considering this, the question I asked all of you at the beginning of the term, consider whether that's either too hot or too cold. If you had to choose one, so unfortunately you have to pick one for this hypothetical question, would you prefer whether that's too hot or would you prefer whether that's too cold? So I am interested in finding out how OSU students feel about this. So what do you think? So what I did is I took that student survey and I found that, let me see, 145 folks preferred too cold. We had 46 folks prefer too hot. And so you add that together and that's a total of 191 folks that voted here. So out of 191 folks, 145 of them said they would prefer too cold as opposed to too hot. So looking here, using our class as a sample, if I want to have a guess for the proportion of all OSU students that prefer whether that's too cold. So I'm going to focus on the too cold. This is my success, right? So if I'm looking at my sample, right away I know I'm talking about a P hat. So I'm going to have my number of successes, so that's 145, because I'm interested specifically in the category where people picked too cold, out of the total number of people in my sample, so 191. I'm going to round a little bit here. Should get about 0.759. So about 75.9% of the ST201 folks preferred whether that's too cold rather than too hot. So that would be my starting point if I wanted to estimate this proportion for all OSU students. So like we did in the sampling distributions and whatnot for a mean, we have our distributions of inference for categorical variables. So we have a population distribution. And you might notice, looking at this, this is a bar chart, right? Because here we have it split into two categories. We have defective, I think these are actually cups, and non-defective, and we have defective. And so in this particular case, they calculated the proportion of all cups that were defective was 0.12. So this is that population distribution. So if I had all the observations that could be observed, I have a certain number of successes and a certain number of failures. And so they have these parameters, they have a mean and a standard deviation. Then the sample distribution. So this is me taking one sample. So if I take one sample, here's a sample distribution. In this particular one, it looks like we took a sample of 200. And of those 200, 0.14 or 14% of them were defective. So this is my bar chart for this scenario. So everything in here, they're statistics. As opposed to when you look at the population distribution, those should be parameters. So then, if we were to take this sample distribution, and let's not just take one sample, let's take many samples. So repeatedly sample. I'm going to take all the unique samples of 200 I possibly can and calculate the the sample proportion for each one of those samples. It would go into a sampling distribution of p hat. And what's great is the sampling distribution of p hat is going to be centered right at p, which is usually what we want to go ahead and estimate or test. And we know the spread as well, because it's that square root of p minus 1 minus p over n. So just like before, we're most likely to have the sampled distribution. So it's usually the only thing we're actually able to observe. We would love to observe the population distribution or the sampling distribution of p hat, which has all the unique samples of that size in the sample proportion from all of those samples. However, when we get one, and it has to be a very good sample, right? It has to be representative of the population. We can use relationships between these two distributions to say, okay, well, we believe the sampling distribution will look like this. So that's it for lesson 32. Join us for 33, where we're going to go ahead and build a confidence interval.